There we go. Okay, so number one, for each of the following diagrams, determine the magnitude and the direction of the net force. Magnitude, direction of the net force in this question. We're just going to go through the homework, because I didn't give you answers.
I didn't understand this question, like the whole one and two. Just confused about it.
Zero.
So it's asking for what is the net force and which way is the net force going. So again, remember, net force is, if we flip back a couple days ago, net force was the sum of all of the forces in the direction of motion. So if there are forces that are causing motion, there's going to be, if there's forces causing an acceleration, there's going to be a net force. So these two forces here are equal and opposite, so they cancel out. They balance each other. And these two forces are equal and they're in the opposite direction, so they balance each other out. So is there a net force on this object here? No. Sweet. Net force equals 0. How about this guy here? The net force here is, and which way?
Down.
You sure?
Fine. Up.
Why is it up?
Because the pointed direction of the force is going up, all the power is directed.
No, but hold on, just look at the numbers. Why is the F net 250? Up.
Okay, it says 400 newtons up on
No, I just understand.
Yeah, because this guy's pulling, it's pulling up 400 and gravity's pulling down 150. So then the net force is the sum of those forces. So it's, this one is, up is positive, down is negative. So 400 minus 150 is going to give us a net force of 250. What's my net force here? What is it and which direction? 175
right.
to the right. F net equals 175 newtons that way. Cool. How about this guy? F net equals 60 newtons going that way. Cool. How about this guy here? F net is 100 newtons which way?
Right.
Cool. And this guy?
55 newtons. What?
This is a tricky question.
It's not already in motion, it's just slowing down.
Oh, maybe it's already in motion. Yes. So then F net is going to be, I like it, 55 newtons, and this guy's going to the left. Cool. So that's question 1. Looking at unbalanced forces, if there are any, and what the direction would then be. Okay, this one. Use the information given from each diagram to fill in all of the missing blanks. So, this block here, we know all the information up here. We know the mass of the block is 5. We're looking for the acceleration. How are we going to find the acceleration?
Well, we know
F net equals ma. So then what is the net force? How'd you get it? 70 to the right minus 20 to the left, so it's that F net's going to be 50 newtons equals 5a. So what's the acceleration? Which way? To the right. Cool. How about this guy here?
For gravity and for normal force.
117.6 what?
Newtons.
Can someone verify? Okay. So that, how'd you do that, Connor?
I just did gravity equals 12 times 9.8.
Yeah. So Fg equals mg. The m is 12, g is 9.8. Gets you 117.6. Fg equals Fn. These arrows are the same length.
I wasn't sure about that.
Well, so forces are vectors.
No, I know, but I wasn't sure about the arrows. Like, 'cause I didn't rely on the arrows.
In this case, there's nothing else to do. That's the only thing you can assume.
Okay, and then the acceleration.
Well, and there's no other forces acting on this object, so
Yes.
the normal force would have to be equal to gravity. What is going on here? Hey, John, what's up? Okay. Okay, is he going to be gone for a while, or? Okay, who's he seeing? Bye. Oh, wait. Tangent. The office is looking for you. Don't know why. So what's the acceleration?
0.
0. Why?
Because everything's going the same, everything cancels out.
All the forces are balanced. There is no net force. Acceleration is 0. Cool. This guy over here.
I got 392 for your gravity, or like the gravity newtons, force of gravity, and the normal force.
How did you find out what Fg and Fn are?
Well, Fg equals mass times gravity, so 40 times 9.8.
Which question are you looking at?
Same one as yours.
Where'd you get the 40?
I made up some numbers. No, because I know the acceleration is 4 meters. per
Okay, so
second.
we've got the acceleration is 4 meters per second squared to the right.
Yeah. So I just times that with math. Oh, sorry. Yeah.
Someone want to help him out?
No, yeah.
Yes,
245.
Jasmine. Jasmine.
Dang it.
I started by figuring out the Fnet.
Okay, so you found Fnet. What's Fnet?
That was 160.
160 newtons.
Yeah.
Because you took this guy minus this guy. 240 minus 80 is 160. Okay, carry on.
And then I did the Fnet equals ma, and we have the acceleration in the Fnet. Then I
60
solved it.
equals m times 4. You found that m equals 40 kilograms. Love it.
Then I did Fg equals mg.
So then Fg equals mg, so 40 times 9.8.
And I got 392.
Love it. Which is the same value Connor got. Connor just couldn't explain it, right? Right? Same values?
I explained it here.
Same values?
Yeah.
Okay. This guy, what's going on here?
Okay. I'm gonna explain it this time.
Oh, Connor wants to try again. Okay.
Fnet. I found Fnet.
How'd you find Fnet?
I got. How does that sound good? Okay. I found gravity first.
Okay.
So I know the box weighs like 8 kg, so I just did 8 times 9.8.
Cool, which is?
For gravity, which is 78.4. And then I just, to find Fnet, I just took 160 minus 78.4, which is 81.6, divided by 8, gives me the acceleration, which is 10.2.
Oh boy, hold on. Acceleration equals Fnet over mass. Is that over 8? Okay, so what did you get for the value there?
10.2 meters per second.
Can someone verify?
Yeah.
Okay, love it.
The
This guy here?
night time. What was it? Okay, 392.
No, someone other than Connor?
Oh, come on, I'm having fun.
No, someone else.
Man, all you do it. Okay. Rise up.
This guy down here.
You got this.
Alright, we're looking at the net force. That has to be 40 times mass times acceleration.
Okay, so Fnet equals ma. A is, or mass is 40, A is 4. Okay,
Yep, and so that's going to be 160.
you betcha.
So that has to be the difference, and because the pi is 200, then the friction has to be 40 for that to make sense.
Cool.
From then, the force of gravity is going to be mg, so 40 times 9.8.
Which we've done before, and that's 392. Cool, love it.
And then stop it.
Sorry?
Just like that.
Okay. And then the last guy here?
Can I answer now?
Nope.
Oh, come on.
Someone else. Brendan, I posted the video last night, right?
Yeah,
Okay, good. It makes sense?
somewhat.
Kind of, sort of? Okay.
Just one question, I didn't do it, but like the last question, the normal force and the gravity are the same
right?
Okay.
Because there's no other forces up or down, so these two have to be balanced. So the FG is going to be 500.
Yeah, and by that you can divide this number by 9.81 and get the.
Right, because FG equals mg, so we know FG, we know little g, so 500 divided by 9.8 is?
Then you can do the acceleration.
No, what is it? What's the value you got?
I didn't calculate it, I'm just doing my mind.
51?
Yeah, 51.
Point.
Oh, 2.
Okay. 51.02 kilograms. So then we've got the acceleration, F net equals ma. What's the F net? 125 equals our mass, 51.02 times a. So my acceleration is what? 2.45? Can someone verify? Okay. Love it. Questions, comments, concerns, any piece of this? Got to make sure that you're able to do this on your own. Okay, flip the page. The other thing I wanted you to take a look at here was the odd numbered questions on this page here. Is there any one of those anyone would like me to go over? All of them? Okay. Did we attempt them?
Yes.
Okay.
I haven't.
Front corner claims they have attempted. Hands up if you, just be honest. Hands up if you attempted all 5 of these and struggled. Okay, so some did not attempt. What's the best way to do this? Okay, so you know what? Let's go through a bunch of these. Question 1 said, and we want to draw these things out. We have a 1,100 kilogram car accelerating from rest to 60 kilometers per hour over a distance of 45 meters. We want to find the net force acting on the car. So let's draw the car. This is question number 1. I'll zoom this in a little bit. I'm drawing my car. There's my, whatever that thing is. There's my car. Let's write down what we know. So we're combining everything we did in kinematics with everything we're doing now in forces. We know that the mass of this thing is 1,100. So what forces are going to be acting on my car?
Very normal force, but it cancels yourself.
Okay, so we're going to have an FG, we're going to have an FN. And we're going to have, we're told in the question that the net force, that we're looking for the net force. So which way is the net force going to be acting on this car? To the right. How do you know that? You said so. Okay, so there's a net force acting to the right. What's the car doing?
Driving.
It's accelerating from rest to 60 kilometers per hour. So that gives us what? It gives us a VI and a VF, okay? VI in this case is going to be 0, because it's at rest. VF is going to be 60 kilometers per hour, which isn't super useful to us in the current form, because we know the distance the thing travels is 45 meters. We aren't told explicitly what to find from this set of information. We're just told to find what the net force has to be.
Yeah, but we know one of the things of net force.
To find the net force, the equation for net force is what? F net equals ma. I know my mass is 1,100,
We're going to get the acceleration.
so I need the acceleration from this kinematic data. So Vf squared equals Vi squared plus 2AD. And before I can shove anything into that equation, what must I do? Convert, Naya says, to what? From what to what? Okay, you're going from kilometers per hour to, because you could go from, oh no, this needs to be in meters per second squared. So 60 kilometers per hour is what in meters per second? 16.6 repeating, or 16.67. Okay, so VF squared is going to be 16.6 repeating squared equals, this is 0, 2A times 45. What's A? What we get? What'd you get, Zaid?
3.08 if I did it right.
I don't think you rounded it right, but yes.
Oh yeah.
Unless I screwed it up. 3.09 meters per second squared, because I also used the repeated value.
I see what you did.
So that's the acceleration. That value is going to go in here. So then what must the net force on the car be given its mass and the acceleration? 3,399.
95 if you use a repeater.
Okay, if I use my rounded value. If I don't round at any point, then yeah, you're right. But that's it. That's number 1. Cool? It's combining everything. It's the free body diagram stuff that we did yesterday with the kinematic stuff that we did last unit. Just step by step, what do we got to find? It's like a puzzle. Shall I keep going? Okay. Angelina, am I just going in order, or is there?
3.
We all want 3? Okay. Let's do 3. What's happening in 3? We have a 950 kilogram car traveling at a constant speed of 35 meters per second. If 350 newtons of friction act on the car, what is the applied force provided by the engines? I don't even have to. Okay, we'll draw this thing out. For the sake of time, there's my car. What are we told about the car?
Car has a speed of 35 meters a second. This is next to the right. And 0 acceleration.
So we're told that's a constant speed, therefore acceleration equals 0. Okay, what else are we told?
Has 350 newtons friction acts against it if you post it up.
Force of friction equals 350 newtons, okay?
And its mass is 950.
We know the mass is 950. I'm just going to put that over here.
That's all.
Question says, what is the applied force provided by the engine? So the applied force must be in which direction? So what's the applied force? Yeah. Therefore. That's mathematical shorthand for therefore. 350 newtons. How do you know?
Well, it has to.
There's no net force. There's no acceleration, so there's no net force.
Yeah.
Therefore, F net equals 0. So then these two forces must be in balance. And we're done. Angelina. How you're confused about how the F applied is? That's supposed to be, that's 50. Because the force of friction is also 350. And because F net, because this is constant speed, acceleration has to be 0, right? If acceleration is 0, there's no net force. And if there's no net forces, all my forces are in balance. So if I have a backwards 350 force, I must have a forward 350 Newton force. Number 5. A student raises their 15 kilogram backpack from the floor at a constant velocity of 5 meters per second. How much force must the student apply? So, let's draw a backpack. Here's my backpack. What forces are acting on my backpack? Gravity, which way? Could we give a value for gravity?
Yeah, you could.
Well, let's do it then.
147 newtons.
How'd you do that?
By 15 by 9.81.
Okay, the mass of the backpack, which we're told in the question was 15 kilograms, times 9.81 meters per second squared is the value for little g. So the force of gravity you said was 147. Okay, what else is acting on my backpack? Sorry? You're picking it up. So there's a force upwards. Sure, if you're picking it up by a strap, we can call this a tension force. I don't care if you call it a tension force or an applied force. Either way, it's effectively the same in this case. What else do we know about the backpack?
It's moving up to 5 meters a second.
The velocity is moving upwards at 5 meters per second. And what do we know about?
Constant, which means the acceleration is 0.
And the implication then is?
So Fa is equal to Fg.
So yeah, then your tension force, your applied force has to equal Fg, because F net equals 0. So that's also going to be 147, which I rounded to 150 down at the bottom of the answers. Right there.
That one's something.
Sorry?
That one's something.
Did you draw it?
I didn't draw it. I didn't draw an up force. I thought it was just gravity acting on it. That's why.
So this you forgot that the student was raising their backpack.
That's because at the time I was thinking with an arm, like that.
Well, that's the same thing. It's still an upward force. If the backpack is being raised, then call it an applied force. Number 7, shall we? A 75 kilogram skydiver falls at terminal velocity, which is 220 kilometers per hour, before pulling the chute. If she slows to 25 kilometers per hour in 3.8 seconds, determine the average force of air friction that acts on her during the deceleration. What is causing that air friction to all of a sudden just show up?
It's the air catching the parachute.
The air catching the parachute. All of a sudden, she's increased her surface area like crazy by releasing her chute. Absolutely. Okay, cool. So let's draw this out. This was our person. This is our person now. Which of these are we going to actually use for our free body diagram? Don't know. What's the question? The question says,
It wants between.
so this picture must be drawn at what point? If this is going to function as our free body diagram, what does this represent?
Parachute deployed, she's stopping.
Yeah, the instant the parachute's deployed and she begins to stop. So she's got an upward force of, we're told, F air. What else is acting on our skydiver? Gravity. We know her mass, so we can figure out what this value is right away. Fg.
And in the moment the parachute opened, the acceleration is 0. So,
Nope, it's going to get real big
okay.
very quickly,
735.75 newtons.
allegedly. That's her mass?
Yeah,
Sorry, that's her weight rather?
yeah,
700 and
35.75.
newtons. Okay, cool. So that's Fg. We want to find the average force of air friction on her during her deceleration. So this is what we want. What else do we know? We know a bunch of velocities. Vi is
220
220 what?
kilometers per hour.
Vf is
25 kilometers an hour.
what else do we know?
She stopped in 3.8 seconds.
So that's our time.
Well, you go between those two speeds.
She dropped her speed from 220 to 25 in 3.8 seconds. Okay.
So we could figure out acceleration.
So we need to find acceleration. Why do we need to find acceleration?
Because that will give us our F net for F air.
So F net equals ma. In this case, what's our F net expression going to be?
F air? What do you
What's going in here for F net? What are the net for? What are the forces acting on her? We've never written it out like this. What are the forces that are acting on her here?
Oh, so it should be like FG minus F air,
It's either going to be Fg minus F air or it's going to be
F air minus.
Fj minus Fg, depending on which direction you want to call positive.
Yeah.
So which way do you want to call positive in this question?
It can be
go down? Or I mean up.
doesn't matter. So
Okay, so if we call that direction positive, then F net is going to be F air minus Fg equal ma. We haven't written it out like this. We haven't had to write it out like this,
Okay.
but now we do. So that's going to be F air minus 735.75 is going to equal her mass, which is 75 kilograms, times the acceleration that we're going to find right here. So then, how would we find the acceleration given this data? VF equals VI plus, if you don't remember, we've got our formula sheets. That guy there. VF equals VI plus AT. So VI is, and we can't use either of these values. We got to convert them both into meters per second. Because our time's given to us in seconds. 61.1 repeating. The 25 is 6.94 meters per second. So we're going to have a 6.94. Oh, and what's the direction here on her velocities? It's going to be negative because we called up positive and she's falling. So both these values need to be negative. So we have negative 6.94 is going to equal negative 61.1 plus A times 3.8. So I'm going to add 61.1 to both sides, and I'm going to divide by 3.8. My acceleration is what? Someone verify? Maya says it's good. So then when you take this value, we plug it into here. How do we solve for F air? Multiply these two together and add this guy over. So F air, I ran out of space, is going to equal what? This times this
1,068.75.
plus this. One more time.
1,068.75.
I'm going to check that.
Whoa.
negative.
1804.8.
The acceleration's upward is positive because this.
Oh, yeah, yeah.
333.
What did you get, Calvin?
Hold up. Let me go back.
I got 1,804.83.
How do I get that?
That's also what I got, which is the correct answer.
How do I go back?
I don't know.
I think it was, I got like.
Why are you using your phone? Use your calculator. Oh, you're using a calculator? It's not your phone? Okay, good. 1,804.5.
I don't know, Storm.
Did you add this value over or did you subtract it?
I subtracted. I got 300.
No, but. So it's this. You were solving for F
I
air.
got 75 times 40. Nope.
Punch it in again.
75 times, what is it?
14.25
1068.75.
plus, we're solving for F air, you have to add this over.
Okay, I see.
Add the 735.75.
Yeah, that's where I went wrong.
There you go.
Thank you.
Like, the FAR is like bigger than the FM, but the sky is going down.
Well, okay, hold on. What's the okay? Okay. It's good that you brought that up, Luis. Let's analyze what's happening here. This F air represents what?
It's the air going into the chute and the drag that it's creating. That's slowing you down.
So she's still falling down. She's just now falling slower. The instant the chute gets pulled, thing goes whoomp. Doesn't take a lot of time. All of a sudden, the force of the air is this on her, dropping her from 220 kilometers per hour to 25 kilometers per hour in a very short period of time. After she's hit 25 kilometers per hour, what's F air gonna what's it gonna be later? It's gonna be less. We can do better than that. It's gonna be what?
Negative?
No, can't be negative. That means F air all of a sudden is pushing down, which means she's speeding up downwards again. That's a problem.
Oh, that's why, like, for example, when you open the parachute, like, you can go up and then go down again.
No, see, this is where your experience with the real world and your experience
Like,
here is fundamentally different. How do you know you go back up? How have you experienced skydiving, Luis?
my father was a professional skydiver.
Yeah, okay, but that's not what I asked. How have you experienced him skydiving?
No, I didn't, like, experience, like, myself doing it.
Okay, so then tell me how you did. How did you witness him skydive?
Videos.
Okay, videos. You watched someone else filming him, and then he pulls the chute. Does he fly up,
Oh, no.
or does he just fall slower and
Yeah.
Buddy with the camera keeps falling?
Yeah, now
So that's the, I mean, and when I pictured in my head, I see the same thing, right? That's because I've never been skydiving. All I've ever seen is you're falling, and now all of a sudden, wham! You're flying up into the air.
Can we calculate what
That would be hugely problematic for you, because you would be going from a large downwards force to a large upwards force. And theoretically, if it's big enough, it could rip you in half. So that's not actually what's happening. The person with the camera continues to fall. The person whose chute just deployed is just falling slower. That's why I was so picky about how you'd experienced your dad skydiving, because of the fact that we just watch it in film, so we assume we know what's going on. So this person's still falling down. They're just falling slower because the parachute, as it's deployed, creates this massive deceleration, but the velocity is still always down. As the velocity slows, remember I told you yesterday, maybe 2 days ago, that air resistance is really quite complicated. And it's impacted by a few things. It is impacted by your mass a little bit, your shape a little bit, also how fast you're going. If you're not going very quickly, there's not going to be a lot of air resistance on you. You don't feel the wind blowing in your hair on a calm day when you're walking. But if you were to start sprinting, you might start to feel it a little bit on a calm day. If you're sprinting into the wind on a windy day, you're going to feel it a lot. So the speed at which you're moving relative to the air is going to be what impacts how quickly air resistance is, or how big air resistance is on you. Yes? We cool with this? Okay. So this is the force of air resistance required to slow this person down. But does a skydiver ever reach zero velocity
Yes.
before they hit the ground?
No.
No, they never stop. They never hang in the air for a little while. That'd be weird. So as she's now reached 25 kilometers per hour, what's going to happen to this force right here? It's going to decrease from this to what? If she stays at 25 kilometers per hour till she hits the ground,
Oh, that's easy to.
it's going to be exactly FG.
Oh.
Because air resistance is really complicated. As she slows down, air resistance is going to slowly get less and less and less and less. Eventually, when she's falling at a constant rate of 25 kilometers per hour, which is totally reasonable speed for a skydiver, when she hits this, this and this are going to have to be the same. Because she's now no longer accelerating downwards or decelerating upwards. 7's a great question. Do we follow the logic here?
Yes.
Okay. 7's a great question.
Horrible.
This is a question like 7 is where you're going to, because you're going to redo all of this again in grade 12, except you're going to do it way quicker, just to kind of give you a bit of a recap on this kind of stuff. This is where you're going to start in grade 12 when you hit this unit. It'll be like, yeah, remember, here's a skydiver. Wow.
Will we see like
Figure it out.
questions like that in our test? Or will
Absolutely you would. Yeah. This is the hardest stuff I'm going to give you in 11 is where you're going to start in 12. So yeah, you're going to see this again. And then there was one more question, and the day is almost done because of the lovely short block. Number 9. I hate these stupid short blocks too, but it's not that much shorter. It's better than Friday. A 1,350 kilogram crash test car strikes a cement wall at 24.0 meters per second and bounces back at 8 meters per second. If it's in contact with the wall for 0.9 seconds, what force did the wall exert on the car? That's a fun question here. So let's draw. These kinds of questions, it's a lot harder to draw a free body diagram for because there's two different scenarios. Hold on. You've got car flying towards the wall, and then you've got crumpled car.
Can we assume the wall is like thick, like it's just not gonna move? Like is that like a factor in the wall is wall? No, not necessarily, because if it was like a sheet of paper, it would go right through.
But it doesn't matter what the wall. It doesn't matter what happens to the wall. You know, all that matters is I tell you the car has bounced back. Doesn't matter what happens to the wall. The car is bouncing back. So the car now has a velocity, a final velocity. It had an initial velocity. In order for this to have, for velocity to change, what must have happened? It has to have accelerated. Velocity was to the right, now it's to the left. So the acceleration is going to have to be which way? We haven't declared anything to be positive or negative yet. Okay, Zaid, which way do you want to be positive? Okay, so if you're saying this direction here is positive, then this thing has to have an acceleration that way. Because it went from an initial velocity to the right to a final velocity to the left. This is interesting.
But if there was no acceleration to the right and then it takes it, there is a change in the acceleration.
But it's not accelerating to the right. We're told it impacts at 24 meters per second. So constant velocity at impact, which is lovely. And if it has an acceleration to the left, then it must also have a force to the left, yeah? So now we just got to fill this thing in with values. What's my initial velocity? Okay, 24 meters per second. What's my final velocity? No. Negative 8 meters per second. What else do we know?
Car weight.
The impact time was what? 0.97? No, 0.9 seconds. Okay? So we can find the acceleration. Connor, you also said we know
Oh, car weighs 1350 kg.
the mass is 1350. Okay? It's my Corolla.
There is FNET.
Sorry?
There is FNET.
Yeah, we're looking for FNet. We're looking for the force exerted on the car by the wall. So, what do we do?
Figure it out.
By doing what? Finding acceleration. Tanjo, was that you? Okay, what's the formula we're going to use to find acceleration based on what we're given?
VF equals VI plus AT.
Let's fill it in. VF is -8. VI is 24. A is what we're looking for, and T is 0.9 seconds. So the acceleration is going to be what?
I got it.
What'd you get?
35.5555555.
5 repeating works. 35.5 repeating. Meters per second squared, and that's got to be negative. Can someone verify that? No, no, you are not good enough. I want multiple people. Zaid did? Okay.
Yes, he did. He confirmed it.
Fantastic. So then to find the force is equal to mass times our acceleration. We know the mass is 1,350. The acceleration is negative 35.5. So what is F net? It's got to be that value right there. Nope, it's got to be that value right there.
Negative 4795.
So 48,000? 48,000 newtons. So the 4.8 times 10 to the 4 newtons that I gave you on the thing.
How oval would the car be? Is the next question.
No, the next question is, if the same car had no crumple zones, then it would bounce back more aggressively. It would be in contact for less time. So the only difference here is that this time would be shorter. You find the acceleration. If the time is shorter, what's that going to do to this value here? It's going to get way bigger. If this value gets bigger, then this value is going to get huge. So I'm not going to do the calculations again because it's already been done. There's no point, and I've spent the entire class just doing all your homework for you. You will find that it went from 48,000 newtons to 540,000 newtons. This is why cars are designed to collapse in on themselves when they hit something. Because without a crumple zone, the force on the car is going to be way bigger because the time in contact is going to be much smaller. So cars are designed to collapse. That's why cars from the
Drop, right?
sorry,
Drop.
I don't know the specifics of how they're designed to collapse, but they're designed to collapse so that the force on you strapped to this machine isn't 500,000 newtons. It's only 48,000 newtons. Like 1/10. You sure it's still going to hurt, but I think it's better than 10 times the force. Guaranteed dead versus now you're in a lot of pain. I mean, some people would prefer the death. I suppose if you're now a quadriplegic, for some people death would be better. I don't know. But there it is. There's number 9. Okay, so that's your homework. Questions, comments, concerns? Naya. Which other ones? The ones that
4, 6, 8.
they are built in. They're in here as well. 1, 2, 3. Because there was 9. There's 11 questions on here, and there's 11 answers down here. That's actually what I was going to assign you right now. Because I just spent the entire block doing all your homework. So if you had a chance, if you didn't have a chance to actually do these on your own, or if you struggled with them, then I want you to, rather than do the next lesson, forget the next lesson, we can do it tomorrow. I want to make sure you guys are good with this. Yeah, I want you to do the evens here. There's 5 questions there because 4 has an A and a B. I want you to play with this stuff. If you haven't already, grab your book and do those last 4. And the answers are in there. There's 11 questions and 11 answers. So that's that. What I want. That's what we're going to do today. We'll do Newton's third law tomorrow. I'll leave this here.
The third law is the
Naya, did you do all 11 already? Sorry?
The third one is the first one. As a action and the reaction.
Yes, that is for every action of the opposite reaction. And this was all straightforward. Much bigger. Did they give you a coil down book at the beginning? Do you want a coil down book? Hey, Khalil. You said 5 minutes early, not 15 minutes early. I'm okay with you leaving early, just when you say earlier. If you'd like some line paper so you're not cramming everything in here, I think that will really help you. There's 3 boxes at the back. On top of that table, they have different color coil books in them. Go grab one, and you'll have paper then for the semester. Desmond, did you finish all of them? Okay, that's what I want you to do. You got time. Good stuff. James.
We have to end the phone for
No, you have to. No. No. I don't want to see the book at the end of the semester. Manuel. I want you to be doing those. I want you to try those. You already did all of them? Impressive. Where's all the work? Sweet. You do what you gotta do. Long day today? Why don't you try this stuff now? Iman, do you want this paper to write on? You should not be cramming everything into that. Evens, because I signed the odds last night. You didn't finish. So you know what? If whatever you haven't finished on that page, that's it. Just put your stuff. Let's go. You did all of them? I'm signing right now the evens. I assigned the odds from this page. The odds, that was your homework from last week.
Where's my phone?
Because I just did all the odds, so I want to make sure that you can actually do the evens.
My guy. Too bad. Too bad.
Yeah, when you go home, you're gonna have an app. Push through. Use this time.
Thank you.
The only one who can nap. Yeah. And Manuel. Because they're done.
I should go.
Did you check your answers with?
I took a picture of it, but I couldn't read it when I took a picture of it. So I just assumed.
Yeah, just, at the very least, just check what's up. What's up here now?
Yo.
Make sure you're good.
Ooh, this is a problem. How's that good problem? Oh.
Mr. Budafios rounded out answers, right?
Yes.
By how much?
What's your value?
255 per quarter.
Yeah, so 260. Yeah. Yeah. To cover all your guys' possible rounding along the way, these things are rounded to the appropriate number of sig figs way back at the beginning. So 260.